Hello, calculus students. Welcome to another online lesson. Today we're going to continue our discussion of 3D vectors, specifically focusing on finding the angle between those 3D vectors using the dot product. And we'll know we're successful when we can solve IB level problems involving dot products and angles. Before we get into the actual angles, let's talk about a scenario where two vectors intersect, but they have essentially no angle or an angle of 180 degrees. If they're on the same line, we say they're collinear. And the rule for finding out if things are collinear, it's very similar to knowing if they are parallel. If you can take some vector and multiply it by a scalar, and you can turn one into the other, you know that they are collinear. And you say, well, how is that any different than parallel? The difference is the two vectors have to contain at least one point the same. So if you have vector AB, and then we're talking about BC, then we're in good shape. If we have AD and then you're talking about DE, they both contain D. And so we need that to have collinear. I don't think this is going to be covered too much in the book, but it's a topic that's come up occasionally in the past. So I just want to mention it. So very similar rules for collinearity and parallel vectors when it comes to 3D vectors or 2D vectors for that matter. Quick review here. For two-dimensional vectors, if we had two vectors A and B with their components as shown, a sub 1, a sub 2 for x and y, b sub 1, b sub 2 for x and y, we have the scalar product, which I often refer to as the dot product, which is just multiplying the x components, multiplying the y components, and adding those together. We notate this as a dot b, and we can use that to find angles as shown in this formula. Cosine of an angle is equal to, again, the dot product right there divided by the product of the magnitudes. Okay, so we've seen that before. How is it different now for 3D vectors? Well, to start with, we've got a third component. We've got our z component. We've got our x component, y, and z. And that's the same thing for both vectors here. So in this case, how would I write the dot product? Well, it's the same idea. We're going to multiply our x components, so that'd be a sub 1, b sub 1, plus a sub 2, b sub 2, plus a sub 3, b sub 3. So again, multiplying our z's, our x's, our y's, the whole kit and caboodle, getting multiplied together and then added up. The same thing we did before, multiplying straight across if they're written in component form and then adding. Now, what about the cosine? Well, we still have the dot product, which I just wrote above, which is a dot b. I always got confused. I'm like, oh, 3D vectors, still two on the top because it's only two vectors. Vector A and vector B, they just have three components each. And then we still just do the magnitude. We've got the magnitude of A and the magnitude of B, which again is still based on the Pythagorean theorem. It just has that extra component getting squared. And last but not least, if the dot product is 0, then the vectors are perpendicular, which means they cross at a 90-degree angle. Very important. We're just going to do one example showing dot product and then finding an angle between two vectors here. Give myself just a little more room. So to start with, dot product. We are going to multiply the x's together, the y's together, and the z's together here. So I'll have two, let me notate it. I've got p dot q. Again, they're vectors, and I'm writing it, so I underline each one. I would have 2 times negative 1, which is my x components. I would have plus 3 times 0, which are my y components, and then negative 1 times 2, which are my z components. Multiply, I end up with negative 2 plus 0 minus 2. So that gives me a grand total of negative 4. So the dot product is negative 4. Now when I go to my angle formula, I've got cosine of the angle is equal to the dot product, and I already know the dot product is negative 4, all divided by the magnitude of each of these vectors. I'll probably need a little more room than I left myself here, so I'll extend my division bar. And for magnitude, I take each of the components in the first vector and square them. So I have 2 squared plus 3 squared plus -1 squared. Important to have parentheses there. And now I do the same thing for my second vector, vector q. I have -1 squared. There is no y component. I'm not even going to write it. It's going to be plus 0 squared. And then finally plus 2 squared here. We are going to go ahead and simplify. I'll bring down my cosine of the angle. I now have -4 over radical. And 2 squared would be 4 plus 9 plus 1. And then over here, I'm going to have 1 plus 4. So bring that down one step further. I've got -4 over radical 14, which doesn't reduce, and radical 5 also doesn't reduce. And not that I'd even want to, because the goal is not to find the cosine of that, but the goal is to find the actual angle. So how do I get the angle alone? Inverse cosine. Again, it's a function. Make sure that you're writing the cosine inverse to the left of it. Squeeze it in if you need to, or you can write it on a separate line. And also be very careful. Now, when I go to type this in the calculator, I need to indicate groups on the calculator. This whole denominator here is a group, so I need to use an extra set of parentheses. And you can type that in now. And on my calculator, if I'm doing degrees, I end up with the angle equaling 119 approximately degrees, and that's rounded to 3 significant figures. And if I want to do radians, I could say that it is about 2.07. And that's the idea. This can be applied to a lot of things, everything from quadrilaterals and other polygons, triangles, angles, all kinds of stuff that we can use this for, or really any perpendicular lines if, again, the dot product equals 0. And I have a few book problems that will further illustrate this. On page 310, numbers 2 through 5, 12, and 15. Again, the farther you get into the problems, the more interesting they get. All right. Might be the shortest video yet. We will see you next class.